chap, and then I saw her in the crowd, and I looked her in the eyes.
Hello, welcome to Wake Up Astronomy. My name is Dr. Luke Barnes. I'm an astronomer here at the University of Sydney. I'm a cosmologist. I study how galaxies form, and in particular, I do massive supercomputer simulations that try to start off with the way our universe started, almost smooth, and then see if at the end of the day, once gravity's made things collapse together, we get something that looks a bit like a galaxy. So that's what I do, but I'm here to answer some of your questions. I have them all here on some cards that I can shuffle for you, so I think we just jump straight into that, and I answer some of these questions. So let me just get them all here. Let's start shuffling the questions, cutting the deck, pick one at random. Here we go. All right, question 1. What would it like to live on one of the binary stars, assuming that the climate is habitable? All right, that's a good question. So if you know your Star Wars, Tatooine is going around a binary star, so it would have two suns, basically. That's a binary star is where there are two stars orbiting each other. And that creates a bit of a tricky situation because in gravity, when there are three things trying to orbit each other all at the same time, things are a bit tricky. So, sorry, I should say who the question was from. The question was from Ada. Thanks, Ada. Things are a bit tricky. So if you get things interacting the wrong way, one of the things can be shot out. So the way to orbit around a binary star is you make sure the stars are over here doing their little thing, and then the planet you make sure keeps a wide berth around the whole thing, and then that's more or less stable. Because we want to be habitable, we want to stay at a nice safe distance from the two huge stars. But what it would be like is basically if there were two suns. There would be sort of two sunrises. They might come up one and then the other, or they might come up together, but it would be a pretty interesting situation to live in. There would be two sunrises, two sunsets, but as long as we're at a nice distance, then the universe, the planet would still get a nice amount of sunlight and so still be habitable. All right, thank you, Ada. Let's go to the next question. I'm going to try and power through these. Next one. Did Einstein ever get anything wrong? The answer is yes. Yes, he did. So famously, there's what he's called the biggest blunder of his life. So here's what happened. He had a new idea about gravity in about 1915, so about 100 years ago. And what it seemed to show him was that the universe as a whole can't be just stars all just spread out to infinity, because the mutual gravity of those would make the whole thing collapse. So what Einstein said was, so what that suggests is the whole thing has to be moving in some way, either outwards or inwards. What Einstein did was to say, oh, that can't be right. Let's put in an extra force to sort of hold back the collapse of everything. And so he included what's called the cosmological constant. Now, the problem was, he called this his greatest blunder, because if he just ignored that and said, okay, well, then the universe as a whole has to be either expanding or contracting, he could have predicted that the universe is expanding, which it is. So that was a sort of missed opportunity. So that's sort of Einstein's greatest blunder, as it's called. The blunder was failing to just sort of see, oh, well, what the theory's really trying to tell him. But later in his career, he tried to put together various theories that came from other bits of physics into one unified whole, and his efforts there weren't particularly successful. So there's a large sort of chunk of the later bit of his career where he tried a whole heap of things that didn't quite work. So Einstein did some wonderful things, but was human like the rest of us. Well, sort of. Okay, great question. Thank you, Liv. All right, let me shuffle the deck. Let's keep going. Ada again. Hi, Ada. Could you tell me if it is possible for our spaceships to exceed the speed of light in the future, and if so, how? Actually, there was another question along these lines I might as well get out. So, is it possible to construct a warp drive? So that's the same sort of question. And the answer is yes, it is possible. So if there's no gravity involved, Einstein's theories tell us you can't go faster than the speed of light. You can't get in a really big rocket and turn it on and start off going, at zero velocity and zero speed and just keep powering on until you go faster than light. That's not possible. But in Einstein's theory, gravity is just the way that space and time warp. So it literally changes geometry, the way the geometry of space and time work. And if you warp things that way, then you get something that looks an awful lot like gravity. So it is possible, says Einstein's theory, to have a type of matter which would create a sort of speed lane through space and time, where instead of going the slow way from here to there at the speed of light or less, you could sort of jump in the fast lane and, thanks to gravity, warp your way to your final destination quicker than you could have if you just went at the speed of light in ordinary space. The problem is the type of matter and energy we would need to create this warp drive is something that we just don't have anything. We're not sure if the universe has provided that type of matter and energy, but if that could happen, it would be pretty cool. One of the problems actually here at the University of Sydney, Corinne Lewis and Brendan McMonigal did a work on this for Brendan's honours thesis here. One of the problems is you jump in this warp stream, any other thing that ends up in that warp stream is obviously moving pretty fast when it gets to the other end, and so it gets shot out the other end of the warp drive at a ridiculous speed, and so there better not be anything in front of the warp drive. It's probably going to get obliterated. So it's sort of half warp drive, half super weapon. But all of this is pretty theoretical at this stage, so we don't have to worry too much about that. All right, warp drives. Totally could happen. Next question. Sorry. What is the universe expanding into? From Sabina. So you may have heard that the Big Bang is described as an explosion, which makes you think of there was this explosion here and then everything got flung out from the explosion. That's not how it's supposed to work. So as I said before, Einstein's ideas about space and time are that space and time can warp, and in particular they can stretch. But it's supposed to be the whole of space and time which does the stretching. So there can't be the universe over here and then empty space out here, because empty space is space. It's part of the universe. The idea of the Big Bang is that the whole of space itself expands. So there's no outside. Everywhere is expanding. Everywhere you sit, you're surrounded by stuff in the universe. And if you look at a distant galaxy in any direction, no matter where you are, you see it moving away from you. But there's no outside. There's nowhere you can sort of sit outside the universe and watch the whole thing expand. It's supposed to be the whole of space and time. So the universe is expanding, but it's not expanding into anything, because if it was expanding into something, that would be part of the universe, right? All right. Thanks, Sabina. Good question. Let me shuffle again. We're powering through these. Next question. How do we know that dark matter really exists? All right, so here's the story. You have your theory about how gravity works, okay? Whether Einstein or Newton, whoever's theory that is. And then you have that theory, you say, here's where the stuff in the universe is. It might be where the stuff in the solar system is, or the galaxies, all of that. If you take this and that and you put them together, you get a prediction for how the stuff in the universe should move, how your system evolves in time, right? So if you apply it to the solar system, you'll get how the planets go around. If you apply it to a galaxy, you'll get how the galaxy rotates or collapses or whatever, okay? So here's what happens if you take your theory and you take where you think all the stuff in the universe is, and the thing you get out, the prediction at the end, is wrong. Well, then one of these things has to change, okay? So the idea with dark matter was we looked at all the stars and the gas we see in galaxies, and we threw that into these equations of gravity, and it doesn't matter if you use Einstein's or Newton's, and what they predicted was all galaxies don't have enough matter to hold themselves together. They should be flying apart, right? Which is not what's happening. So what we think dark matter means is that actually we've missed something over here, as well as stars and gas and all those gas clouds like the ones you might see behind me there. There's something else there in the galaxy. It doesn't shine into our telescopes, but it's still there because it's holding the galaxy together with dark matter. So that's how we infer that dark matter is there. There's other bits of evidence that might suggest that suggest that it's there as well. There's way that galaxies make light bend as it goes past them. That's another thing due to Einstein's theory of gravity. But that's why we think dark matter exists. This relates to a question from Steve. Thanks, Steve. Is dark matter necessary to explain the observable universe, or is some modified theory of gravity more feasible? So I said, remember, it's this theory plus here's where we think the stuff is, gives the prediction, and we've had to change the amount of stuff. We could also change the theory. That's not the preferred way that we think dark matter, the galaxies, could be explained, because all the ways to change the theory, which would successfully explain how galaxies actually move, are a bit ugly. They're a bit sort of hacked together and they have too many bits and pieces and bobs and odds and ends thrown in. They're called modified Newtonian dynamics, or MOND. There are people looking into these things, but those theories don't seem to explain other things about our universe, and they seem to be a bit sort of hobbled together. So we think it's probably dark matter at this stage. All right, good questions. Let's power on. Question from Matt. What is the most distant object that has ever been detected? Well, that keeps on changing, so I kind of had to look that up, but thankfully we actually got a seminar here at the University of Sydney on Friday from one of the guys who's doing this work. The most distant object, as a sort of one singular object that's been detected, is a galaxy, and it's from a time, so the total history of our universe is 13.8 billion years. It's from a time which is 0.4 billion years after the beginning. So at that time, the universe was about 10 or 11 times, I guess it's 12 times, it's redshift 11, 12 times smaller than it is today. So it's an extremely early times. It's just a galaxy. We don't know much about it because it's so far away, it's kind of hard to see. But it's there. We see from the light that it's a awfully long way away. So we have time for one more. Is that what we're doing? Excellent. Let me just have a look. Sorry. Last question. Sorry. Of the day. Oh, yeah. Question of the day. I'll answer one more and then say it's that one. Okay, good. I'm going to pick one that I like. Not doing this at random. Okay, another one from Ada. Are silicon or mercury-based organisms possible? If they are, under what circumstances? So this is kind of interesting. You're carbon-based. We're all carbon-based, right? So all the DNA, all those interesting molecules that you're made out of are based on carbon, one of the elements. So there's a question of, if we're thinking of life elsewhere in the universe, could life be based on other elements in the periodic table? If you think about the periodic table, the ones that are most similar are vertically above or below each other. That's why it's laid out that way. So the one that's most similar to carbon is silicon. So the question, could we make silicon-based life? Could there be silicon-based life? At the moment, we don't know. We obviously haven't made it, because life's kind of a complicated thing. It's not likely. Here's a reason why. If we start with carbon, we can join carbon together in really fantastic ways to make all the interesting molecules of life. So, for example, if you just take carbon and hydrogen, the simplest of the elements, right, and you say, how many different kinds of molecules can I make just out of those two? Right, I could stick 4 on, that's one. I could stick carbon together and then stick some more hydrogen on. Turns out there's about 70,000 ways to make a new molecule from just carbon and hydrogen. So carbon is phenomenally versatile. Silicon isn't. You can only make about 55, right? So 55 different chemicals versus 70,000. Says that probably silicon, it may not have what it takes. So that's why we think actually silicon-based organisms, we're not entirely sure. So let me go to the question of the day. I think it's this one. I think what did Einstein get wrong is a great question to ask, because we're constantly trying to test these ideas to see what would happen. So asking what a particular person got wrong is a very good way of trying to understand how science moves along. So that question comes from Ada, who wins an astronomy goodie bag. The question was an excellent one. So is it time to sign off? I believe it's time to sign off. So thanks very much, everyone, for coming along. I hope you enjoy the rest of these. There's plenty of these on for the rest of the week. So think of more questions, and we'll see you next time.